So good afternoon, everyone. I'm Junwei Lyu from the University of Queensland. I'm currently a second-year PhD student, and I would like to first express my thanks to the Institution of Structural Engineers to give me this chance to talk about my research project. So the topic of my research is optimal design of an efficient floating windbreak. We start from looking at the Global Risks Report of 2018. The report has listed the top 5 global risks both in terms of likelihood and in terms of impact. Among all these challenges, we can see that extreme weather events and their accompanying effects have consistently taken up 3 places in recent 3 years among the top 5. It is quite evident that they are reshaping our life and bringing us challenges that we have never encountered before in our history. This can be well evidenced by our experience in recent years. Starting from 2016, a severe thunderstorm impacted Brisbane, leaving the port of Brisbane and the airport a complete mess with disruption to the transport. And later in 2017, Cyclone Debbie damaged lots of Queensland's most famous iconic islands and infrastructures. This can be glimpsed from the transformation of the Shield Harbour. And as the most vulnerable and sensitive part of the world to the climate change, the Pacific Islands have already taken actions to adapt to the rising sea levels. They are now pitching their hopes to the arising new concept of floating city. The concept is quite promising. However, they first need to deal with the problem with huge waves and high wind speeds. It is quite evident that we can't embrace the idea of a floating city without solving the problem of the wind and the wave. So my research project looked at the problem of the wind. There's another one ongoing for the wave. Actually, we already have a type of object that is exactly designed for this purpose, which is called windbreak. A windbreak is a barrier that protects human beings and their activities from wind-induced losses and damages. Windbreaks can be categorized into vegetative windbreaks and man-made windbreaks. Vegetative windbreaks are quite effective, but they are not flexible enough to satisfy our needs, which leads to the development of the man-made windbreaks. Man-made windbreaks often present in the form of fences. Over time, windbreaks have gained lots of popularity among the people. We can see them being built for power plants, for farming, for lines, and recent years have seen new types of windbreaks arising. So inspired by these windbreaks, we proposed the idea of a floating windbreak. So by utilizing the flexibility of man-made windbreak while mimicking the beneficial characteristics of natural windbreaks, several rows of hollow tubes are added on top of an inclined surface of the concrete platform to act as a windbreak. Due to its appearance, this can also be called artificial forest. The entire length of the structure is around 1 kilometer. The height from the bottom is around 52 meters, and the width is around 45 meters. So by building such an efficient floating man-made windbreak, we hope to reduce the wind speeds at 30 meters high by 20% during storms when placed 1 kilometer away from the protected structures. So in order to achieve this aim, we divide our project into several objectives. The first one is to find an optimal configuration of the platform and an ideal layout of artificial trees by maximizing the sheltering effect and reduce the wind speed by 20% through numerical analysis and wind tunnel experiments. And then we are going to measure and compute the wind loading on the floating windbreak to guarantee the safety and reliability of the windbreak itself. Finally, we would like to propose a semi-analytical and semi-empirical wind speed prediction model to provide an easy-to-use designing guideline for the windbreak industry. So to design a windbreak, one must first have an understanding of the wind flow around the windbreak. Here we adapt the division by Jude et al. So very far from the windbreak, the wind still doesn't see the influence from the windbreak. It still maintains the low profile. We call this region approach flow A1. When it gets closer to the windbreak, the wind profile becomes a little bit distorted, we call this region approach flow A2. And then it separates into two parts, one part bleeding through the pores and one part going above the windbreak. We call them displaced flow B and bleed flow C. And behind the bleed flow region, there's a quiet region, and behind that, there's a very large mixing region E. So when the wind gets further away from the structure, it returns to a local profile, and in this region, we call it the re-equilibrization zone. So here we show the extent of each area with respect to the windbreak height h. I also reviewed the key parameters for the windbreak design. All the parameters can fall into two categories, the windbreak structure and the approaching wind characteristics. So the height is the most important parameter. The protection area is proportional to the height. When the height is set, the porosity becomes the most important one. An optimal value exists between 0.2 to 0.5. And the pore characteristics, like the size and shape of the pores, will also alter the protection of the windbreak. And for multi-roll windbreaks, overall the networking between the multi-rolls will provide us with better protections, and the role of spacing, widths, and configurations still needs more investigation. As for the approaching wind characteristics, the obliquity of the wind will generally deteriorate the protection of the windbreak, and the instant turbulence, here we means the roughness length, will change the shape of the wake. And during our discovery, there's a surprising finding that although there's a need for windbreak, we are lacking engineering guidelines to design a windbreak to assess their performance. So now we only have 5 models for predicting the wind speed behind the windbreaks. Here I listed the applicable range of each model, the wind speed component they are targeting at, and the type of windbreak they are designed for. And comparing the input parameters of the models to the key parameters for the windbreak design, we can see that all the models only consider part of the key parameters for the windbreak design. And in the following slides, I'm going to show you the detailed performance of each model. So we start from looking at the mean wind speed after a single roll windbreak. So X in the figures means the distance behind the windbreak, and the Z is the height from the ground. The vertical axis on the left figure means that the mean wind speed at 0.5 h normalized by the mean wind speed at the same height in the approach profile, and the horizontal axis on the right means that the local mean wind speed normalized by the wind speed at the height of h in the approach profile. We can see that among the 5 models, for the horizontal profiles, the ESU model and the HER model generally capture the trends of the data sets, and the other models didn't. And on the right-hand side, we can see that the only 2 capable models generate more conservative results, with the ESU model goes closer to the data sets. So for this case scenario, we think that the ESU model performs the best among all the models. And we move on to see the mean wind speed of the multi-roll windbreaks. So here we show you an example of the horizontal profile of mean wind speed at a certain height. Now the figure becomes more scattered, and overall home model is slightly better than the other ones. Before 10H, all the data fall between the prediction lines, but after 10H, there's underestimation of the mean wind speed. So we don't have winning choice for this scenario. As for the wind speed fluctuation after a single roll windbreaks, here we define the turbulent intensity as the standard deviation at the height of h, normalized by the mean wind speed at the height of h in the approach profile. So on the figure on the left and in the middle, we can see in the nearly and the middle, the ESU model roughly captures the characteristic of turbulence, and it is the only model that can predict the wind speed fluctuation after a single roll windbreak. And on the figure on the right, we can see in the Farley, it needs reconsideration. And overall, the prediction results are generally too conservative, so there's also no winning choice for this scenario. Given the fact that all the models provide us with the estimation of the wind speed reduction in the lee, we move on to use the CFD to do the analysis to find the optimal configuration of the windbreak. So we choose the domain size and the boundary conditions according to the best practice guidelines. And we build a mesh based on the principle that high resolution grids are needed in the area of interest and the area where large gradients of flow exist. And we use ANSYS software, ANSYS as the software for analysis of 3D steady flow for the two-dimensional flow. And we choose K omega SST model as the turbulence model. We use simple algorithm for the solution scheme, and all the terms are discretized in a second order. And the model is scaled down for 100 to facilitate the comparison with the wind tunnel experiments later that's going to be conducted later. And for the verification, we eliminate the discretization error by grid sensitivity study, and we make sure that the horizontal inhomogeneity is not affecting our results by running empty domain tests. So here I build a model for a typical segment of the floating forest to test the effectiveness of initial design with tubes. And here I show you the typical dimensions in the model scale. And in the simulations, all the residuals have satisfied the criterion listed in the best practice guidelines. So here's the contour plots of the mean wind speed behind our initial design. Here, the mean wind speed ratio means the local mean wind speed normalized by the mean wind speed at the same height in the approach profile. So it generally tells you how much percentage of mean wind speed is left in the location. For example, 0.8 and 0.7 in the figures means that 20% mean wind speed has been reduced from the approach flow. And we can see that the 30% reduction area extends to 800 meters, while the 20% reduction area extends far beyond 1 kilometer. And then we move on to do the optimization. Considering the volume occupied by the platform, we take the platform as our first target. So we build several cases with different front angle, but the same freeboard height and the same structure height, the little h and the big H. And we look at the mean wind speed of the wind flow behind these windbreaks. So in the figure, we can see that when increasing the front angle theta before 50 degrees, more reduction will be introduced. And after 50 degrees, the reduction remains to be quite similar. So we can draw a conclusion that there's an optimal value existing between 50 to 90 degrees. And similarly, we also look at the effect of freeboard height with several cases of different freeboard height, but the same theta front angle. And in this time, we can see that the mean wind speed ratio is not changing when we change the freeboard height. So in a dimensionless sense, we would like the freeboard height is not affecting the wind speed reduction in the leeward area of the windbreak. So the research is still ongoing, and in this stage, we can draw the following conclusions. The currently available wind speed prediction models only perform well for mean wind speed behind 2D single row windbreaks. There's a lot of work to do behind multiple windbreaks for predicting the mean wind speed, and there's also lots of work to do for predicting the wind speed fluctuations. And the initial designs will provide us with a 20% mean wind speed reduction area, extends to 30 meters in height and 1 kilometer in length. And there's an optimal front angle existing between 50 to 90 degrees. From the wind engineering perspective, the vertical freeboard could be removed. And the future research will be conducted to find the optimal configuration of the floating windbreaks for maximum protection while controlling the capitalized expenditure and the operational expenditure. Thank you very much for listening.